everybody for the second talk of this morning. So that will be the second part of Bernard's talk on tensor decomposition.
Thank you. So I will not recall what we discussed yesterday. I will go straight to the decomposition of tensor and sequences. So what do we mean here by this decomposition? So for matrices, the decomposition can be a decomposition where we can read the rank, for instance, using a singular value decomposition. So it's a product of matrices here, n by r, here a diagonal r, and V transpose, where V is also m by r. And this is what you get when so U and V are unitary columns, and they are also the eigenvectors of this m transpose. And SVD, when you use SVD, you get in fact a way to compute the best low rank approximation of the matrix. When you truncate the, so usually when you have a, say, a null matrix, you will have here full diagonal. The matrix will be a full one. But if you truncate and put some zeros there, you will get the best rank R approximation. This is well known. So for tensors, we have a similar kind of decomposition. Here, a multilinear tensor of order 3. We want to write it as a sum of so Uj, Vj, tensor Vj, tensor Wj, where these are vectors, so Uj, J in and Wj in the different spaces. So we want to find it in a finite decomposition such that the R is minimal. So that we have seen also. In terms of coefficients, this is just saying that the T I1, I2, I3 is the sum of this UI1G, U1G, I2G, WI3G. And in terms of polynomials, it is like saying that the multilinear polynomial T of X is the sum of the product of linear forms in the variable x1, x2, and where the coefficients of this linear form, they are in fact the columns of the matrix, the matrices U1, U2, etc. About symmetric tensors. So what do we, when we talk about decomposition, we, so symmetric tensors or homogeneous polynomials of degree D or forms of degree D, given by this representation in the monomial basis. We have here coefficients, yes, alpha, x to the alpha, with a multi-index notation. So we want to represent this as a sum of a weighted sum of powers of linear form. So here we have a linear form to power t and the weight omega n. Just notice that this representation, you can scale here the point to I and put the scale to the power d in the weight, so that this is not a unique representation, but so we can normalize the representation. For instance, if this coefficient, this first entry is not 0, we can scale so that this 1, and have a representation where the points are starting with say having 1 as first coordinate. So the rank here will be the minimal R so that we find this weighted sum of powers. Talking about moment sequences, so here we have a moment sequence up to degree D, and we want to decompose it in this way where we have here weight omega I and this evaluation at poles Ci for this exponential Ci scalar Z truncated in degree D. This corresponds, as we have seen, to the decomposition of the form as the power of weighted sum of powers. So there, this transforms into a decomposition of sum of exponential, weighted sum of exponential, truncated in degree. Because we have seen that if you remember the evaluation, the power of linear form is so its dual is the evaluation at this point, and this translates in the Z variable, the dual variables, as an exponential. It's linear. So the moment sequence decomposition will be in terms of weighted sum of exponentials, and we can also consider polynomial exponential decomposition, where here we allow to have a polynomial in Z times an exponential. And we will see this decomposition appearing also. So this is a rank of the sequence when R is minimal. So R here is the number of exponentials we have. And here, the polynomial exponential rank is not the number of exponentials, but this, yes, I didn't define it. So the sum of dimension of the space spanned by all derivatives of this polynomial. So you take this polynomial in Z, so Z1, Zn, and you derive it with respect to Z1, Z2, Zn. Repeat it, repeat the derivation. So all derivations you can take. So Z1 square, Z2, and so on. So this spans a finite vector space. You compute the dimension. You take the sum of all these dimensions, and you get R, which is, when it is minimal, this is called the rank, the polynomial exponential rank of the sequence.
I'm sorry, once again, I'm struggling a bit. Sigma is long.
Sigma is this moment sequence.
Yeah.
We represent it as a series. Okay.
And then omega I is, so omega I before was a constant.
Yes, this is a constant.
And now you associate the constant.
But now, no, we look at decomposition where this is not a constant, but polynomial. So it's a richer decomposition. And of course, when we have this decomposition, then the dimension is the number of omega n. I mean, the rank here.
So it's allows you to find the dimension. The dimension of the.
Yes, this is the
The
space.
span of what?
I forget to put the definition here. This is a space spanned by all derivatives you can make with this polynomial in Z.
And that square bracket is still the truncation.
Yes, because this is this exponential series, which is here,
It's
infinite. So I truncate it in degree because this is up to degree.
What is this kind of decomposition?
We will see. So it's called polynomial exponential decomposition. Polynomial exponential decomposition
I see that's the name
of the series.
Okay.
So, but I don't tell you what how it is related to the tensor yet. I just want, but it will be. So, a geometric point of view, the Veronese variety, you have seen it in the talk of Alessandra, called the normal curve when we are on P1. So this is the variety of weight times the power of a linear form. Good. It's we look at the say here the affine variety, but it's a projective variety. It's smooth. Projectively, it's smooth, and finally, it's a cone which is smooth, except at the origin. So when we talk about the decomposition of the form as a weighted sum of powers of linear form, we simply say that F is in the sum of points, each point living in this Veronese variety. The second variety that was related to the border rank in the talk of Alessandra is in fact the closure of this sum of varieties. You get an algebraic variety, which is called the R sequence, if you take the closure of all these sums. In terms of when you are talking about measures and moments and sequence of moments, we have here, and yes, to simplify things, let's consider measures defined on a set S, which is the subset of Rn and compact. So the positive measure supported on S is space, which is used in polynomial optimization or approximated by moment hierarchies polynomial optimization. This is in fact the convex hull of the Diracs for the points in S. These Diracs, as we have seen, they are the same as the evaluation in terms of linear functionals. They are the same as the evaluation at the points. So our positive measure, you can see them as the convex hull of all this cone generated by the evaluation. And when you truncate these linear functionals in WD, so you get truncated moment sequences of measures supported on S. And this is the same as the convex hull of these powers of linear. So here we have a point which is with first coordinate. If we go back to the projective setting, like taking a point with the first coordinate equal to 1, and x0 equal to 1. This is like the power T of a linear. So the picture is this is giving some geometric intuition of what we have for this cone of truncated moment. The geometry here is in picture. So for the sequence, we can imagine that the Veronese variety is the red curve. In fact, we have the rays from this point on this curve. When we take an element in the 3 seconds here, it's like taking a point which is in a plane spanned by red points. Take all the plane and all points on the plane spanned by this ring. So this defines a point in the sum of these varieties. when we take the closure, we allow the points to move and to go close one to the other. So then you get a tangent, and you have planes spanned by tangents or other faces, and we take points on this plane. When we consider this, it's one, for instance, the same, but we take just a convex combination. So like here on this picture, we have a triangle, and we take a point inside the triangle. So it's a convex body, convex set made from this Dirac's or evaluations or powers of linear force.
Why do you put it measures?
Measures? I mean, it's not a definition.
Yeah.
It's a notation. So when measures, they are defined as well, in analysis, classical way. For instance, Lebesgue measures. And so when you have measures, you can look at what is called the Riesz functional, which is associating to a measure a linear functional. And we represent this linear functional by its moments. And so we see measures as linear functionals, that is vectors of moments. Moments which are infinite. In fact, when you have I think it's Riesz theorem, it's saying that a measure is uniquely defined by its moments. It's a correspondence between measures and vectors of moments, infinite sequence of moments. And this is the way we see it. So these are Dirac's measures or evaluations, which are this linear functional. So we are living in this space of the dual space to the ring of polynomials. And we take here the convex hull of this evaluation. Yes? As usually. So you take the convex combination of points in the set. Finite, you can take the finite combination of Sorry? I mean, for vectors in the space, so you can. So yeah, so you have a vector space of measures. You can take the sum of measures. When you have positive measures, you take the convex combination of measures. It's a convex, again, it's a positive measure. So here is what we do. We do so here it should be the ray spanned by this Dirac's, but the convex set spanned by this Dirac's, by this measure. So we can, when S is compact and we are in a nice situation where this is closed and it is compact for some norm when you bound the mass, the total mass. So when you bound the moment one, then it's compact. Okay. Now the question is how we decompose a tensor or a moment sequence. In fact, what we would like is to have matrices which can reveal the rank of the tensor this decomposition. And also a way to deduce the decomposition from this matrix say, associated to a tensor or a moment sequence. And so we go to flattening or matricization in some literature. It's also called like that, or catalectic or Ankiel matrix or moment matrix. So they're all the same objects. So for multilinear tensor flattening, so what Alexandra presented already, it's a way to say that when you have, say, an element in this tensor product space, you see some groups of tensor products here as a vector space. And so you have an element here, which is, in fact, an element in this space, E tensor F. And this is a space of matrices, and so you have a matrix associated to it. For symmetric matrix tensor, it's a bit more different, but in fact, it's the same. But we use here the apolar product. So you remember, here we have a form of degree D, and we look at the matricization in degree K, D minus K. So what we take is this Crank matrix of F with monomials of degree D, which are the product of monomials of degree K with monomials of degree D minus K. So we take all the apolar product of F with this monomial. And this defines the flattening of F, also called the catalectic or Ankiel matrix associated to F in degree K, D minus K. When we have measures and moment sequences, so F here should be replaced by moment sequence of a measure. The Ankiel or the moment matrix associated to this mu is the integration of monomials of degree less than D, which are the product of monomials of degree less than K times monomials of degree less than D minus. This is a classical moment matrix. And we can refine this construction instead of degree K and D minus K. We can take subset A of polynomials of degree K, B subset of polynomials of degree D minus K, and then we have Graham matrix for the set AB, the Ankiel matrix, which is made from the apolar product of F with the product of A times B with A and B. This is a matrix. It's representing some operator. Which operator? So here there is a difference with the talk of Alexandra. So, and I think this has avoid some complication in the analysis of the properties of these matrices. So what is this operator? We have an operator, an Ankiel operator, which is going from a ring of polynomials of degree D, the vector space of polynomials of degree D minus K, to the dual of polynomial of polynomials degree K. In the presentation of Alexandra, it was in fact a map going from the dual to the space of polynomials. And then you have the dual variables U, which represents the differential, which were used. So here we work from the final space to the dual. And what is this space? This map. Simply, you take the product of a form of degree G minus K with F star. F star is a dual to F. And so this is a linear functional defined on the dual of polynomials of degree K. But it's simply the product. So it's in fact a very simple operator. Okay. A word about the
Just since you mentioned it at the end, you end up, accepted defined over infinite space, while before I defined over some
here it's the
classic
degree
but
it's
the
homogeneous degree D minus K.
end you get the transpose of the matrix space defined.
Yeah, I mean the matrices are the same, but its interpretation is in terms of an operator from polynomial to dual, and not the transpose.
The circle of the comparison.
Yeah, so there are some notation convention to fix, but here you see K minus K. Maybe you have K minus K K. So it's the same matrix, but you interpret it. But you can interpret it in this way. So some word about this matrix factorization. When we have so first definition of a van der Monde matrix, we have points, one CR in K to the n. We have polynomials, A1, AS. So we define the van der Monde of A with for the point C as the value of A1, AS at the point first point, and so on, the value of A1, AS at the last point. It is the van der Monde of A for the point C. What we can see quite easily is that when we have a factorization of this decomposition of this form, omega I times the C scalar x to the d, so the linear form. Taking mk to be the monomials of degree k, we have a factorization of the Yankian matrix associated to F in degree k minus k in this way. So it's the van der Monde mk at the point C, where C are the points. One, yes, there is a typo here, Ci, C1 CR, times the diagonal of the weights here, times the transpose of the van der Monde in degree D minus C. That is. So when we are looking for a factorization, a matrix which is revealing the rank of the tensor, so the R here, this could be a good candidate, provided that this van der Monde has the full rank. When the van der Monde here has the rank R, which is number of points, then we see that the matrix is rank R, and if we can find a decomposition with van der Monde and the diagonal matrix. So if you remember, we have the SVD for matrices. We have U, the diagonal term, and the transpose of V. So here it's similar, except that we ask a structure, a specific structure on the factors, which are they should be van der Monde matrices. And this space of van der Monde matrices is in fact an algebraic variety, but it's quite it's non-trivial to describe. Okay, let's let's take an example with a Fibonacci sequence. So we have here all the Fibonacci numbers up to, we take the degree, here degree 4. So you have seen the correspondence between monomials, tensors, symmetric tensors, dual elements, moment sequence. So here we go from the moment sequence to the tensor. This is the natural way to. So we have this tensor, symmetric tensor, which is in fact taking this monomials of the taking the binomial coefficient and the sequence value. Yes. So this is a tensor. We want to decompose it. We look at the Hankel matrix associated to the tensor, which is this by definition, and it's in fact sigma I plus j, where I and j are that's 1, 2. Easy to see because when you take when you take -1, -1, and 1, you have an element with the kernel. And this is exactly the recurrence relation we have between the terms of the sequence. And this gives a factorization in terms of Van der Mourrain, where we have here C1 square, so the Van der Mourrain for the monomials degree 2, so there's 1 x square, and here 1 x square. So the factorization like that, where we have the 1, 2. The diagonal with the weights we have seen before. I have not them here, but okay. And then the transpose of the Van der Mourrain. So this is Van der Mourrain factorization for the tensor, for the Hankel matrix. Okay, the Xi again. So they are the roots of this polynomial x squared minus x minus 1, so the golden numbers, which correspond to the elements in the kernel of this Hankel operator. The Hankel operator now is going from polynomials to the dual, so its kernel is a polynomial. Is in the space of polynomials. So we will use these ideas to, yes. Sorry? I add this binomial coefficient here. And the way I do it is you want the F star to be the moment sequence somehow. And so when you see how we have defined the F star, and yes, because we are here in a sequence which is indexed by I, and we are putting it in the homogeneous setting. So we have x0 and x. Yes, this is, I put it in one line, meaning I have sigma 0, sigma 1, sigma 2, and so on. I don't index it by multi-indices. Yes. Yeah. I mean, moments, if you say moments, if they are coming from measures, yes, not necessarily, but the sequence of value. Okay, so we will find this decomposition via linear algebra, always using simple linear algebra tools. So for multilinear tensors, this is the tensor, volume of values we can see it slice by slice. And for each slice, you have a matrix. And when, so here, special, when R is the rank of this tensor, also the dimension of the slice here, then the factorization, the decomposition like that, implies this decomposition of each slice. So Ti, the slice I, is the matrix U formed by the columns of Uj times the diagonal of this Wj K times the transpose of the V, where V are the columns are formed from the columns Vj. But this is
This is an
explicit.
assumption. You're assuming that you're in a case where the flattening has the same rank as your tensor.
Yes. I'm saying for T such that we have this. But this means that the slices are active. You just do the computation, expand, see that it's this factorization in terms of matrices. And so what we can observe is that if this T1, for instance, is invertible, so you invert T1 and you multiply Ti by T1 inverse on the left, or you multiply on the right, and then you multiply on the left here by T inverse. And you can see that U is a matrix of common eigenvectors of all these Mi. Just from this form. So how you Ti inverse, you see, you will fill this part, and then it will be a diagonal term, and then will be U inverse. And so you will have a Mi, which is U, the diagonal matrix, U inverse, which means that U is the vector of eigenvectors of the matrix of eigenvectors of Mi. And so we have common eigenvectors for all these slices, all these matrices. Sylvester approach presented by Alexandra. We have here a binary form in variables x0, x1 with its coefficients Pi binomial Pi times. So this can be written as a weighted sum of powers of linear forms if one can find an element in the kernel of this Hankel matrix, P0 to 1 PR. So this represents a polynomial. We compute the roots of this polynomial. So here we are in the projective setting. So the roots will be k beta k. So we have a factorization of P in this form. And the alpha k beta k, they are exactly the coefficients which are. This is what Sylvester proposed in 1851. But in fact, before, Pony proposed a very similar approach to decompose the function signal f of t in a weighted sum of exponentials. Here we have we want to write the function ft as some omega I, which are scalars, exponential of zeta I, like the signal we see. So this is Pony. Okay. So what he proposed? He proposed to evaluate this function in post points 0, 1, 2, and so on. So you get values sigma 0, sigma 1, sigma 2. You make with that Hankel matrix, so up to some R. R is the number of terms you want to find. Then you shift to sigma 1 up to sigma plus 1, and so on up to sigma minus 1. So a matrix which is R by R plus 1. Compute the kernel of this matrix, get the polynomial P of X, which roots C1 and CR are of the form exponential of zeta 1 R. So we take the log of this root, and these are exactly the frequencies which appear in the exponential. So you have a way to, and then you find the weights by solving this van der Waals system times the weight equals the different values you have. So you see, very connected to Sylvester approach, and in fact, it's essentially the same because it's the same problem. We see here that solving polynomial equation is at the heart of this technique. So I will briefly review the classical techniques for solving polynomial equations. And using linear algebra. So how to solve a polynomial in one variable with linear algebra techniques. What you can do is look at the multiplication by the variable x modulo f. So here we assume that we have a polynomial f with a leading coefficient, which is it's a degree d polynomial, and the leading coefficient is equal to 1. So we have the multiplication by x, which takes the p modulo f and compute x times p modulo f. So, well, we know that the quotient of modulo f, the vector space of dimension d, spanned by plus 1 x minus 1. And when you look at the multiplication by x in these bases, you have, so you multiply 1 by x, you get x, so 0, 1, 0. X by x, x squared, so 0, 0, 1, and so on, 0, 0, 1, for x minus 1. And x d minus 1 times x is x to the d, but x to the d is also minus the sum of fi xi. And so you recover here minus f0 minus f minus 1. This is the classical companion matrix associated to f. I guess you have seen it already several times. And you compute the eigenvalues of this matrix, and you get the roots. So why do you get the roots? When they are, suppose we are in the simple case where we have the case where we have simple roots. In fact, this multiplication matrix operator, when you express it in terms in another basis, which is the Lagrange basis, you have a diagonal form where you see the roots on the diagonal. So the eigenvalue, and this shows that the eigenvalues of this operator, which is equivalent to this one matrix, has eigenvalues which are good. So there is this result saying that the eigenvalues of the multiplication by x are the roots ci. The eigenvectors, they are in fact the Lagrange interpolation polynomials, because it's the diagonal form, when the roots are simple. Some words about duality. We can look at the transpose of this multiplication operator. What is it? It's In fact, the transpose operator is defined on the dual in linear algebra. And what is the dual of the quotient by F? So it's a space of linear functionals defined on polynomials, which are orthogonal to F and all the multiples of F. So they are orthogonal to the ideal generated by F. A star, the quotient, the dual of the quotient is this space. So F, the ideal F orthogonal. That is the linear form which vanish on all polynomials in which are multiple of. Okay. So now when we look at the transpose character, I think going from A dual to A dual, it's taking a linear form and computing. We multiply by x. So here it's x star lambda. The product we have already seen, which is the natural product which exists in the dual when we have this product in the primal space. You can call it the co-product if you want. It's defined in this way. And so we can ask what are the eigenvectors of this operator, transpose operator. So a simple check is we can check easily that when we look at the evaluations at the roots, they are in the orthogonal of F. And they form a basis of the dual space, A star, basis which is dual to the basis of interpolation of the interpolation polynomials, the Lagrange polynomials we have seen in the case the roots are simple. And in fact, these evaluations, they are eigenvectors of the multiplication, the transpose multiplication facts. It's a proof in one line. Just take the definition. What is the transpose times the evaluation applied to the evaluation? It's x star this evaluation. What is x star? X star is a linear functional which is taking a polynomial and computing the product by x and then evaluating at the root ci. So it's ci times ci, and this is obviously equal to ci times the evaluation at the root. So we see very easily that these eigenvectors are the evaluation. A word with some relation between van der Monds and an interpolation polynomial. This is also classical. We have our basis of the quotient, which is 1x to the d minus 1. And we look at the van der Monds of this basis at the roots. So the matrix V. The interpolation polynomials, the Lagrange interpolation polynomials U1, U2, they have a representation in terms of these monomials. And we call this matrix U. By definition of the interpolation polynomials, we have V transpose times U, which is the identity. This is saying when we evaluate UI at Cj, it's 0. When I is different from J, and it is 1 otherwise. So this gives this relation. V transpose times U is the identity. Okay, so now in dimension n, the same story. We have the same story. So we consider here an ideal I in a ring of polynomials in n variables R, such that the solution of I is finite over the algebraic closure, which means that the quotient R modulo I is finite dimension. This is called an Artinian algebra. So this algebra is of dimension R and supposed to be finite. So we can look at the multiplication by some element G in A and the transpose defined in the same way, so G star lambda. And we have the same theorem. The eigenvalues of the multiplication by G are the value of G at the root. For instance, if we take for G x1, for the eigenvalues, we will get the first coordinate of the root. The common eigenvectors of all these operators of multiplication, transpose, are, so they are in the dual. What are these linear functionals? They are the evaluation at the root. So we take all these operators, they are commuting, so they share common eigenvectors, and they are these common eigenvectors, they are the evaluation at the root up to a scalar. When the roots are simple, all these operators are diagonalizable, and the common eigenvectors are the interpolation polynomials Qi at the root. Same story. And when the roots are not simple, then we have we use the primary decomposition of the ideal. So here the roots are C1, CR prime. The primary components associated to each of these roots are Qi, R prime. We have a decomposition of the Artinian algebra A as a direct sum of local algebras A1, A2, AR prime, where II is identical to the quotient by the primary component, Qi. We have a decomposition of 1 in this sub algebras, U1, UR prime, and these are like the interpolation polynomial, but when you have multiplicities, they correspond to idempotents, which satisfy the property that UI square is equal to Y, and they are orthogonal in the sense that when you make the product UI uj, it's 0 with this quotient, when I is different from J. Implying that all these operators of multiplication, they have a decomposition diagonal blocks corresponding to each of these subalgebras. And each of these blocks is upper triangular, where you read here the multiplicity of the root and the value of the G here at the root. So this is quite strong properties. You have a way to construct a common triangular form, upper triangular form for all these operators of multiplication, if you choose correctly the basis. Now some words about the dual of A. So you recall this polynomial exponential series, where we have the omega IC and these exponential terms. They are, in fact, series or linear functionals. They are living in the dual. We call the inverse system spanned by polynomials omega I here, space spanned by all derivatives of this polynomial. So I of any power here alpha, any partial alpha with respect to V, and any index. So the structure of the dual of this Archimedean algebra is as follows. You have the dual A star, which is the direct sum of some vector space Di, which is some inverse system spanned by polynomials, finite number of polynomials omega I here. Using this representation of the dual with the binary C times some exponential at the root. Yeah. And the dimension of this space is the multiplicity of A. We can read from the dual representation, in fact, all what we need to analyze these points. So I take an example here. Two polynomials in two variables in the ring of so C of x1, x2. We can check maybe by Grobner-based computation or any technique that the quotient of R by modulo I has a basis which is formed by the monomial 1, x1, x2. In fact, the idea is also the same as this idea, which is obtained by doing some rewriting of the generator. So dimension 3, we look at the multiplication by x1 in this basis and find easily that we have this, so 0, 1. For instance, 1 multiplied by x1 is x1, so we get 0, 1. X1 multiplied by x1 is equal to x1 square. X1 square is equal to x2 because we have this equal 0. So x2 is 0, 0, 1. And so we get these operators, these matrices in the basis V. The common eigenvectors, there are two eigenvectors up to a scalar, which are 1, 0, 0 and 1, 1, 1. You can check easily that there are common eigenvectors the transpose operators. So this represents the evaluation at points. Which point? We have the basis, which is this 1, x1, x2. And this is the evaluation at some point. So when we look at the evaluation represented in the dual basis, what we do is take the basis B, so the coefficient would be the basis B evaluated at the point. So this will be, this vector 1, 0, 0 will be the value of B at the point. So what is it? The point 0, 0. So here we have x1 and x2 dual. And so here we have the point 1, 0, 0. Here we have the point 1. So from the eigenvectors, we read directly the coordinates of the solution. Okay. So, well, we can check that we have here primary decomposition with this primary components for 0, multiplicity 2, and 1 with multiplicity 1. The local algebras are of dimension 2 and 1. The orthogonal of I, or the dual of A, is Q1 orthogonal plus Q2 orthogonal. That is this inverse system spanned by Z1 evaluation at 0 or exponential 0, 1. And this is the evaluation at 1, 1 or exponential Z1 plus Z2. And we see that it's in fact inverse system spanned by Z1. We take Z1, its derivative with respect to Z1 will be 1. So we have here inverse system spanned by Z1 times the evaluation of the exponential at, which is what the theorem was saying. Now, we want to analyze this from the Hankel matrix or the catalytical flattening. And I record here some old result by Honecker, which was stated in terms of Hankel operators, which was defined on a finite sequence of verbs and by a correlation like that, for sum of n plus n. So this is in fact the same operator as the Hankel operator we have seen. And he proved that this operator has a finite rank. Here we have infinite dimension. You can have a finite rank. If and only if we can find representation of the series sigma z constructed with this way, sigma n zn over n factorial, in a way which is this way. So a polynomial here omega I times some exponential and moreover the degree of the omega I plus 1 is equal to the rank of this operator. So what is this degree plus 1? In fact, well, it's what the space spanned by all derivatives of this univariate polynomial omega I, which is of degree of this degree. When you derive it, you will have all monomials from 1 to the degree, all, well, you will have, yes, you will have the same space as the one spanned by all monomials from 0 to degree of omega I. So this is like the dimension of the inverse system spanned by omega I. So this was generalized for n dimension. We look at the Hankel operator going from the ring of polynomials to the dual and taking simply the product of P here, polynomial, with a sigma, which is a linear functional defined on R. And this operator has a rank R if and only if it can be written as a weighted sum of exponentials with weights which are polynomials. So it's a polynomial exponential decomposition. Weights omega I which are polynomials, and this exponential in some points Ci. And what is the rank of this operator? It's the sum of the inverse system spanned by all this omega I. So the dimension of all of the space of, say, taking all derivatives of the omega I, as we have seen already. Moreover, we have that the kernel of this operator is an ideal. Check. You multiply if P times by 0, then PQ times sigma with 0. The product is commutative here. And you have an associativity. So this is an ideal, and the zeros of this ideal are precisely the points which are here. Moreover, we have a primary decomposition of this ideal as Q1 intersected with QR prime, where R prime is the number of points, and QI orthogonal, so this which is the dual of the linear functionals which are 0 on Qi is in fact the inverse system of omega I, this way, times this exponential. And we have in particular this property that A sigma is, so what is A sigma? A sigma is a quotient of R by I sigma, is Gorenstein, meaning the dual is generated by a single element, which is in fact sigma. So it's a rank. It's a free module, A sigma free module of rank 1. Saying A sigma dual is equal to A sigma star sigma. And this is if you look in the local case, it also means that the inverse system is spanned by a single polynomial. If you are familiar with the local analysis and inverse system. So now we are coming back to our tensor decomposition problem. And we assume we have a decomposition of F, our form, as a weighted sum of powers of the Xi scalar x to the d, which means in the dual, F star is the weighted sum of evaluations, say, truncated in degree d. And we will assume also that the first coordinate of this point, Xi, is 0. So we are in the projective setting with n+1 variables. Then we go to the affine setting, assuming that the first coordinate of the point is 1, and we substitute x0 by 1. So we have the ideal of polynomials vanishing at the points, which is called xc. The quotient by this ideal, which is axc, which is of dimension r, which is the number of points. So this is well, standard. And so what we can deduce from the Hankel matrix. So here we assume we have some maybe A and A prime will be monomials of degree k and b minus or less than k and minus k. So the flattening of this F. So we have this decomposition we have seen already. So now what we can say about this matrix, when we assume that A is a set of monomials, for instance, contains the basis of the quotient. A sigma is a quotient algebra, and we assume here that A sigma has a basis which is a subset of A or A prime. Then the kernel of this operator is in fact the ideal of polynomials vanishing at the roots intersected with the space spanned by A prime. And the image is of this operator. So this image is in the dual. It's the orthogonal of this ideal of points. So the orthogonal are linear functionals restricted on the space A. We take the restriction of these linear functionals on this space spanned by A. And it's also the image of the van der Waals so up to operation on the rows, on the columns of H, we can transform this matrix H into the matrix V. Okay.
So here you still have this hypothesis.
Yes, so the
The
strong
rank of-
hypothesis is this one. That this A and A prime contains the basis of.
But also that the rank of the platinum number of the so R, you see one of this R. You want that this R is also the rank of the platinum.
Yeah. But yes, this will. So as a consequence, we have a basis here will be of size R, which is the number of points, because this is of dimension R. And this matrix will be, in fact, of rank R also. Because
Yeah, if you have R defined, then the matrix is rank R. But if
no, I'm not saying that. I'm saying that if we have a basis here, this matrix will be of 1. I'm not saying if the rank is R, there is a basis. So is it? No, maybe
go ahead.
I didn't answer.
I try to explain.
So we have defined this operator H lambda or sigma for any linear functional, as we have seen in Kronecker theorem. So there is this map taking multiplying by lambda, and this map H is going from polynomials to the dual. So we can look at what is the Hankel operator of G times lambda. We multiply by G, and the lambda. And so what we are wondering, what could be this Hankel operator? So just going from the definition of subjects, we can see that it's the same as either we multiply first by J, so modulo the ideal, and then we apply the operator, so H lambda composed with Mj, or we apply H lambda and then we apply the transpose operator of multiplication by G. But this is just because we the effect here on lambda. So we see that these operators, they are appearing naturally when we look at this multiplication of sigma or lambda by some G. So this will allow us to recover the roots, because if you remember, from the multiplication operators, we can get, by eigenvalues or eigenvectors, we can get the points, the solution of our system. So here we have the first proposition. When we have sets B and B prime of size R inside the A and A prime, R is the dimension of the quotient by the kernel, by the ideal generated by the kernel. So so if these are bases of the quotient, then the block indexed by this B prime and B is invertible. And the converse is also. So if this is invertible, then the B and B prime are bases. If we have moreover the property that when we multiply the B by variables, we stay in A, then we can look at the matrix, the Hankel matrix associated to B prime, our basis, and the shift of B by xi. We multiply by xi. These are new polynomials, and we look at remember this Ankel matrix is like a Graham matrix where you collect the polar product of the polynomials indexing the rows and columns with H. So we can compute easily this matrix. So we have the property that Mi, which is inverse of H0 times Hi. So this would be like multiplying by this inverse here. We get, in fact, the multiplication by xi in the basis E modulo of the quotient modulo the points. And moreover, we have this, so we deduce from this, because here we have simple roots. The ideal, the quotient is by the polynomials, the ideal of polynomials vanishing at the point. So this defines the points with multiplicity 1. We have a joint diagonalization of each block Hi, which is this block, where we have E times the diagonal of the coordinates I of the roots times F. So a joint diagonalization of all these matrices, and this also means a joint diagonalization of all these H0 inverse times Hi. So we come back to our example with the Fibonacci sequence. So we are in dimension 1 here. So projectively, we have variables 0 to 1. The tensor is this one. The catalectical Ankel matrix flattening is this. Degree 3, 3. So we are here at degree equals 6. It's a rank 2, still a rank 2. Easy to check. So we look at H0. H0 is the first block indexed by the monomials 1 and x. So because we have substitute x0 by 1 and replace it 1 by 2. So 1x here, 1x. These are the B and B prime. This is the block H B B prime of F. It's invertible, so we have a basis of the quotient. We look at the shift by x. So we take these monomials 1x, we multiply by x. So we will have x and x squared. H1. 1, 1, 1, 2. We multiply it by the inverse of H0, and we get 0, 0, 1, 1, 1. And here you recognize the companion matrix of the polynomial x squared minus x minus 1. This is, we multiply the basis 1x by x, so we have 1. And now we multiply x by x squared, but x squared is equal to x plus 1. It's the polynomial, the characteristic polynomial we have seen. So its eigenvalues are the roots of this polynomial. They are golden numbers, and the eigenvectors, they are these polynomials, correspond to these polynomials, x minus pi, with this scaling factor. And we can see that computing, we get the weights which are given here. So we have this decomposition of the tensor. Okay, I skip this example. Yeah. And I want maybe to, no, okay. Maybe this one will be, no, okay. Here is some application. In the case of multilinear tensors, in phylogenetic. But we can see that the same techniques apply. So we have some species, and for example, here there is an ancestor with 3 species, and in phylogenetics, people are interested in analyzing the gene of these different species, and we can see they appear. So we have here 4 letters, A, C, G, T, and we look, and there are some ways to measure what is the probability that the J A1 appears in S1, S2, and S. So we have, in fact, a tensor of probabilities, P of I1, I2, I3, associated to these 3 is measured. And it is known that, or it is modelized in a way that, so since they are coming from the same ancestor, there are some relation between the probabilities of, we have a gene I1, knowing that in A there is a gene K. And this relation, they are expressed by Markov matrices, which are giving the probability for each species in the transition from A to S1 or S2 or S3. And so these probabilities that we observe gene in S1, S2, S3 can be represented as a sum of some weights times this first column, so the probability for all K from 1 to 4 that we observe I1 in the space S1, knowing that we have K in space A times the probability for the space 2 and times the probability for the space 3. So this is the formula we get. But in terms of tensors, it's like saying P, this tensor, is a weighted sum of so these weights times UK tensor VK WK, where UK, VK, and WK are the columns of these Markov matrices. And so the game here is to recover these Markov matrices from the tensor. So we'll do a tensor decomposition. It has rank 4, sorry. And the decomposition will give us the Markov matrix. So I'll show you here a session in Julia. You can, it's a Jupyter notebook, so you can recover it from this GitHub repository, where you will find material for all the courses of this week. So you can access there, look at the notebook and run it if you install Julia, for instance, and these packages. So here we use a package, well, tensor deck here is not needed, but it's a package we developed for decomposition of tensors, dynamic polynomial for multivariate polynomials, and linear algebra is the basic one. We have some functions here to normalize things which are not interesting. So here it's an example where data are randomly constructed. We have random matrix A, B, and C. These are the factors of these are the Markov matrices. We normalize them to get Markov matrices, and we compute the tensor, which is the tensor product obtained from the sum of tensor product of columns of the different matrices. So this is the tensor. Okay, so we have slice 1, slice 2, 3, and 4. It corresponds to the polynomial which is here. Yes, and sorry, the polynomial. So what we will construct first is slices H0, H1, which is a shift by some variable x1. So yes, how to interpret this? The slices here are the HI, but it's coming from this flattening of associated to our tensor T, where we use, in fact, variables which are xi, 0 to 3, to index corresponding to the first index, and then yj for the second index, and zk for the third index. So this is a polynomial representation. So the polynomial, we substitute the x0, y0, and z0 by 1 to be in some affine sharp of in fact p3 times p3 times p3. So that's what we do in this polynomial. We compute the flattening for the monomials A, which are here, and A prime, which are the product xi, yj times zk, and we get this 4 by 3 matrices corresponding to the blocks here put one after the other. So the faces put one after the other. So when we can check that the first block is invertible, and we have a basis which is formed by the monomials indexing the columns which are here. So 1, y1, y2, y3. And so the multiplication by zi here, also, when we shift this block by 1, it's like we multiply by z1. We shift the block by 2, we get here the multiplication by z2. And the same for z3. So this hi, which is a block corresponding to I here, 4 by 4 block, times the inverse of h1, which is the first block, is in fact the multiplication by yi. So I will be a bit late. Yes, maybe I need 2 minutes to put this example. So we compute this mi, which are the multiplication by yi. We take a random combination, compute the eigenvectors, and get this. And so we verify that these are eigenvectors of all these common matrices mi by taking the inverse of E times on one side and E here, and look at what we obtain. So we see that they are diagonal, numerically diagonal, because this is very small, 10 to the minus 16. But on the diagonal, we have some non-zero terms. So we take all these terms on the diagonal to form the matrix W, which correspond to, as we have seen, the common factorization are common terms on the diagonal term gives the factor W, which we normalize and get this. The eigenvectors, they are computed, the E, they correspond to the interpolation polynomials in the basis. So when you transpose and invert it, you get the Vandermonde at the points. So we do that. The Vandermonde in this basis will be value we are looking for. So this inverse transpose is amount. We normalize it and get 1 on first coordinate, and we get this factor, which is corresponding to the y. So we have the z from the w, the v is the y, and now we have just to get the u, and the u they are obtained by fact this because we have taken the x0 to be the z0 to be 1, we can see that the u is also here. So we have this decomposition for u of ui tensor vi for the block h1. And so since we know v, we get the u. And this gives the terms in the decomposition. We compute the weights by solving the Vandermonde system as here and get the decomposition. And we can check that we get the u, v, w and the weight, and we compute the tensor from this, normalize the difference from the initial tensor to the T1 and get an error which is very small. Okay, so I think this show you how these techniques of operators of multiplication and eigenvector computation gives decomposition of tensors in case where it's not solving the general problem. It's in cases where the rank is not too small. And there are many open questions. So this method doesn't apply for rank which are high. So there are questions like compute the specific rank of some tensors. So for instance, tensors of multiplication of matrices that we have seen. Compute rank or generalized rank of matrices, border rank, cactus rank. How to find best low rank approximation of tensors. These are options where we have we don't know a lot, and there are a lot of place for investigation. Okay, so thank you. That's it.
There are one quick question for Bernard before lunch. Yes, Didier.
Can you make sure that the weights are positive in the last example?
Yeah, so when you know that the Ankiel operator is semi-definite positive, you can ensure that the weights are positive and the points are simple.
The points are simple.
Simple, yes, and real. So it's a very strong condition, which is the case when you have moment when you do polynomial optimization. Because the kernel
It's definitely not same.
now because the matrix is semi-definite positive. When you have a square, it's in the kernel, and the polynomial is in the kernel, and then the kernel is radical. So you can prove that the kernel is radical. So the points are simple.
Okay, so let's find Bernard again.